Hello, everyone. So today we're going to be picking up where we left off with atomic molecular orbitals and hopefully trying to bring everything together. So far, we've built up the various structures of our molecular orbitals and some rough ideas for energies. So what we're going to be trying to do is use that classic of pictorial techniques, MO diagrams, to talk a lot about the energies of molecular orbitals, how they fill, and how we can use them. So this is really bringing everything together. So I want to start this lecture with something a little bit different than usual, a quick review. So when we have built up our MOs, we've done so by using analogous atomic orbitals. And so again, mostly what we've talked about so far has been homogeneous diatomic molecules. So I've got two atoms of the same type, and that's it. And because of that, they're going to have identical atomic orbitals on the neighboring atom. And they'll both be contributing with equal probabilities to the resulting molecular orbital. Gotta love symmetry. So when we're doing this, let's quickly recap who combines to make what. So our low energy 2s orbitals on each of the atoms will go ahead and combine to make a set of 1 sigma orbitals. So the 1 simply represents these are going to be the lowest energy sigma orbitals because we've got another set coming. And they'll come in two varieties, bonding with Girard symmetry and anti-bonding with Ungerad symmetry. So two atomic orbitals come in, two molecular orbitals exit, one low energy, one high. A very similar thing is going to happen with our 2pz orbitals. So these are the ones that are making direct head-on contact. They're going to end up forming, again, a low energy bonding and high energy anti-bonding molecular orbital. Now, our remaining 2p orbitals, specifically the px and the py, are going to go ahead and mix to form a set of intermediate bonding and anti-bonding MOs. So again, make note, in this case, the bonding has Ungerad symmetry and the anti-bonding has Girard. So watch out for that switch. It can be a little messy. So we can use this to bring all of our orbitals together to get an idea about energy. So we're going to leave out the 2s for now and start with a recap of where we left off. Because again, even without knowing any details about the distance or overlaps, here's what typically our MOs are going to look like. The sigma orbitals with the much better overlap will tend to go the bonding will tend to go very low in energy, and consequently, the anti-bonding has to go very high in energy. And then we have our degenerate pi orbitals essentially in the middle, with the bonding with a little bit of overlap going down a little and the anti-bonding going up a little. And this is the classic picture you're used to seeing in, say, general chemistry and a lot of more general chemistry texts. This is the classic description of a diatomic mixture. But as we also brought up last time, I have to worry a little bit about how these will end up mixing with my s orbitals. So again, my s can mix a little bit with my sigma orbitals because they can do that same kind of direct overlap, but energetically they often stay apart. And so what we can do is, again, using what we know about the extent of overlap and the actual starting energy of our atomic orbitals, because my molecular orbitals often don't move too far in energy from the starting atomic orbitals, we can build up a rough description of what my molecular orbitals look like for a general system. So again, my MOs are always going to be centered around the energies of my atomic orbitals. And again, so my ending energies won't get too far away from my starting energies. And the closer in energies these states are, essentially the better overlap I have. And it's overlap that can also really dominate. So that classic overlap integral, as if I have a good overlap, like I do in a sigma bonds, the bonding goes way down and the anti-bonding goes way up. And so again, my first sigma orbital is going to be much lower in energy simply because my s orbitals are lower in energy. And the further away these guys are from each other, the more separate these two species can be. So in general, the sigma bonds coming from my s orbitals will be lower in energy, and then the sigma coming from the p, then the bonding pi, then the anti-bonding pi, and then, Lord help you if you ever have to fill this, the anti-bonding sigma, because this has some serious hardcore clashes and repulsions. So using this energy, then we can go ahead and use Aufbau. If I know how many electrons each of my atoms brought to the table, I know how many electrons are in my molecular, start low, fill high in pairs. And so if I've got 6 electrons, the filling is super easy. 2 electrons in 1 sigma bonding, 2 electrons in 1 sigma anti-bonding, 2 electrons in sigma the second sigma bonding. After that, it gets a little bit messy because I have 2 pi orbitals of identical energy. Hund's rules come into place. Put in 2 more electrons, they both go up. Put in 2 more electrons, they have to fill out the shell, and so on and so forth. So honestly, once you have the actual diagram, a lot of what we know from atomic orbitals carries over astonishingly well. Now, here comes part of the trick, because we run into a problem that all of this assumes that my s and my p orbitals are well separated. So if I'm dealing with 3s, 3p, 4s, 4p, so on and so forth, this is always the case because the z effective in between these two is huge. But when I'm with lighter elements, like my second row elements, so boron through fluorine, these guys get a little bit closer than I would like. And here's going to be part of the problem. The lighter my atoms, the more similar these guys are in energy, and especially the more similar that my s antibonding and my p bonding sigma orbitals get really close in energy. And this is especially problematic because of the fact that they are also physically close. So if these orbitals are close in both energy and physically, I can have some mixing in between these two. And what ends up happening is as these two mix, my anti-bonding orbital goes down in energy. So it wants to separate from my bonding orbital, and my bonding orbital in that p is going to gain a little bit more s anti-bonding character and go up in energy. So I'm going to have essentially stolen some of that overlap. And this ends up being a little bit problematic as it can increase the energy of that sigma bond to such a point that the pi bonding orbital is now lower than the sigma bonding orbital for the p orbitals. So this is a little bit messy because as soon as this orbital's filling switches, I have to reconsider how I fill up. As soon as the orbital energy switch, I have to reconsider how my orbital filling switches, because now my pi bonding orbitals are lower in energy than my sigma bonding. Now, it is worth noting that while we are often focusing on the energies, this is also going to include some actual changes in the orbitals. So as these two orbitals, my 1 sigma bonding and my 1 sigma anti-bonding, my 2 sigma bonding, they start mix, this guy is going to end up gaining a little bit more p character and a little bit more bonding character. Meanwhile, this guy is going to gain a little bit more s character and a little bit more anti-bonding character. So you do have access to some computational methods. You want to have fun, go ahead and try using a Hartree-Fock method on something like a dicarbon species or a diboron species, and you're really going to see this. But in general, what we're seeing is that because as I have lighter elements, these two orbitals end up increasing. The gap in between these two orbitals decreases for lighter elements. We're going to see more of this mixing the lighter the element gets. So thus boron is a classic point in case. But right now, this all kind of feels a little bit arbitrary. So let's walk through let's go ahead and walk through all 8 of these molecular orbital energies for all 8 of my second row elements. And when we do this, again, walking through dilithium to difluorine, what we're going to find is, in general, all of my molecular orbitals will decrease in energy as I have an increasing nuclear charge, or Z. So the heavier the element gets, the lower in energy all of these orbitals get. And the reason for this is actually fairly straightforward, because my atomic orbital energies are also decreasing, because my Z effective is bigger. So of course my atomic orbital energies are decreasing, and thus, because my molecular orbitals are centered on those atomic orbitals, their energies are decreasing as well. And you're going to notice for things like my sigma antibonding and my 1 sigma bonding, I have a fairly steady decrease as I'm in energy as I'm going down. And you'll see this a little bit in the pi antibonding. The pi bonding, because of its overlaps, not quite as much. But the real oddball here is this 1 sigma bonding. So again, this is that bonding orbital generated by direct overlap of my PZs. So when I'm in something like lithium, it's stolen a lot of the antibonding character from my the antibonding orbital generated by my 2 S's overlapping. So that ends up sending the energy for that 2 sigma bonding orbital way up. And this guy is going to be very hard to fill. But as I walk across the periodic table, my S's and P's separate more and more. So what ends up happening is that the 1 sigma antibonding character decreases only a little bit for this first couple shells, because most of that decrease isn't going to the antibonding. It's essentially the 2 sigma bonding gaining some of its character back. And so it starts dropping much faster while this guy kind of steadies off, until a point where you get a little bit more of a kind of even decrease, and a lot more until you get to such a point that while up here, that 2 sigma bonding orbital is almost as high in energy as the pi antibonding orbital. But by the time you get to fluorine, we're back to the order we would have expected if the 2s and the 2p's didn't mix at all. And so we're back to that logical energy separation I expected. Because again, I have this 1 orbital just bucking the trend and changing its relative position a lot. And the real critical point is that transition from nitrogen to oxygen. So in nitrogen, that sigma bonding orbital is slightly higher in energy than my pi bonding. But by the time I get to oxygen, that sigma bonding is now finally lower in energy. It's back to where it should be based on simple principles and not having to worry about the messy mixing in between these 2 sets. So again, the greatest effect in these changes is going to be in this 2 sigma bonding orbital. So in general, the classic take-home message is the same as we saw in is the same exact message we saw in general chemistry. If I have an element of nitrogen or lower, then expect the sigma orbital to be higher in energy. If I'm looking at a element of oxygen or heavier, and yes, this does include everything from sodium and heavier, once you're in third or fourth row elements, their p orbitals will also show the classic behavior we'd be expecting. So at that point, then yes, we should be filling the sigma bonding before we fill the pi bonding. So a little bit too many words, but hopefully the visual trend helps illustrate this. Now, one of the questions is, why should I care? Well, one of the reasons why is that we can then take each one of these molecular orbital sets with its energies, and we can use this as I fill up my electrons to determine a lot of information about bond strength. And the classic metric we use for bond strength is bond order. So when I'm talking about things like first order, second order, what I'm really actually talking about is a metric of the bond strength, because that's all bond order really is. So mathematically, we generate bond order as a stand-in using this idea of it's the number of electron pairs trying to attract the two atoms towards each other versus how many electron pairs are trying to repulse the atoms away from each other. Or in terms of individual electrons, which you'll see the importance of in a little bit, it can be thought of as the number of bonding electrons, so how many are pulling the two nuclei together, minus the number of anti-bonding electrons, how many are trying to push them apart, divide by 2 to turn from electrons to electron pairs, and there you go. That's bond order. So the classic case of demonstrating how this works, as well as why it's important, is the bond order of O2. And yes, I made a mistake on these slides, but let's go ahead and look at the bond order of O2. So at this point, most of you already do know it's second order. But a good way of looking at this is I have two oxygen atoms that are going to mix together to give me my classic set of 8 MOs in the classic ordering. Yay for oxygen, it's the first one that does that. But that means I have a total of 12 electrons to put into these 8 orbitals. So let's walk it through. First 2 goes into sigma bonding, second set goes into sigma anti-bonding. Third set goes into the second set of sigma bonding, and then both the third, or the fourth and the fifth set go into the pi bonding. Now this leaves me only one pair of electrons left, so they go into the pi anti-bonding. 1 electron each, gotta love Hund's rules. So first of all, the obvious thing that's an important takeaway is that my molecular orbital diagram correctly predicts the fact that it turns out oxygen as a molecule ain't a singlet. It's a triplet because we have 2 unpaired electrons, and now you know what a triplet means. By the way, this also means that oxygen is magnetically active. Yeah, that actually is a very useful trick in some fields of science. Not incredibly magnetically active, but magnetically active nonetheless. It's also fairly reactive because it can, from a certain point of view, be considered as a diradical species because these electrons are not paired, which means it's going to be a lot easier for them to come in and go out. Now, in terms of trying to turn these into bond orders, let's count up our electrons in bonding orbitals. So we have 2, 4, 6, 8. 8 in bonding, and then 2, 4 in anti-bonding. This gives me 8 minus 4, 4 divided by 2, classic bond order of 2. So there's only so many molecular diatomic molecules, so this isn't maybe the most useful thing, as you could probably just memorize them. But when we go to more complicated molecules, it turns out these same idea of diagrams will apply, and that can be seriously useful. But one of the other things is this is a quick metric to look at what happens when I try and look at molecular ions. So let's go ahead and consider I have oxygen. So here's my filled molecular orbital diagram. What happens if I pull off an electron and I go to an O2 cation? So this often happens if you have, say, photoelectric excitation, atmospheric chemistry. This guy's decently common. So one of the things that what will end up happening is I'll steal a single electron off of this guy, generate a nice doublet species. Who doesn't like one of them? And more importantly, I still have those 8 bonding electrons, but now I have 3 anti-bonding. So 8 minus 3, 5, divide by 2. Congratulations, we have a bond order of 2.5 in this case. Yes, half bond orders are possible. And in fact, they get quite common in a lot of molecules, especially when you're talking about intermediate species, and metals can get metal complexes can get a bit weird. So turns out that an O2 cation has a 2.5 bond order, which means very likely I just decrease the distance in between my 2 atomic centers. Yay, I just made a stronger bond. This doesn't mean a more stable molecule, but it will likely mean that these 2 centers are going to take a little bit more energy to break apart. Again, because I haven't filled an antibonding orbital. So it's going to be, that's less energy that has more energy that's located in here, and I get less of a head start. But additionally, we get this closer distance. Now let's go the other way. Let's say I start with oxygen, and because oxygen's an electronegative little son of a gun and it likes picking up electrons, what happens if it goes to an O2 anion, which again happens fairly frequently in a lot of metallic and catalytic chemistry. So in this case, I put an extra electron in that antibonding orbital, which means I still have my 8 bonding electrons, but now I have 5 antibonding electrons. I just made my bond weaker as I went to a bond order of 1.5. So that's an interesting fact of how adding an electron can decrease the stability of a molecule, because I've added extra electron repulsion without that electron actually bringing the 2 atomic centers closer. So let's amp this up a little bit more, and let's make it a dianion and go to O2 minus 2. This is a peroxide type molecule, and the reason why is because I put 2 more electrons in that antibonding orbital, giving me 8 bonding, 6 antibonding. I have a bond order of 1. This is the definition of a peroxide, an OO bond at a single bond order. These guys are quite reactive because I made that oxygen-oxygen bond even more unstable than it already was. So when you're trying to make oxygen into a reactive species, which is great for things like catalysis, here's a great place to start. But again, it can be a little difficult putting 2 electrons in that antibonding orbital, so thus changing the surroundings and metal catalysts. But a very important point of a lot of this is that by changing the number of electrons in the species, so by changing the charge, we can actually change the bond stability. And it turns out that molecular orbital diagrams are a really quick and dirty way to illustrate how that happens. So, especially because a lot of energy chemistry and a lot of biological chemistry includes passing around small diatomics like N2 and O2, and even F2 or chlorine 2. These things can be quite useful to understand why we start to see simple trends. Not to mention, you can eventually extend this to larger systems. So that brings us kind of to the end of molecular orbital diagrams, but next time we need to get a little bit more into the energy. Specifically, this idea of we have now ordered our MOs in terms of energetics. But how do I know exactly what these energies are? One of the most straightforward approaches is to use experimental data. Next time, an aside into spectroscopy. Till then, take care and stay healthy.